I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on waves on a string, transverse and longitudinal wave pulses. So in this series of videos, we're going to talk about mechanical waves, which is transverse longitudinal sound and light waves. In this video, we're going to talk about waves on a string, specifically transverse and longitudinal wave pulses, heavy emphasis on transverse wave pulses. So what a mechanical wave is a disturbance which propagates through a medium with little or no net displacement of the particles in the medium. So we're going to talk about transverse wave pulse, which is a traveling wave in which the particles of the medium move perpendicular to the wave velocity. So here we have a string, and we can see that we have a pulse traveling through. This is looks like a bump traveling through the wave. So if we look at that, a still picture of it, we see the direction is moving to the right, and the particles of that wave are moving up and down, so perpendicular to the direction of the wave. So the ones on the right side start moving up. As they get to the highest point, they stop, turn around, and then start heading back down. And all that happens is it moves back and forth. Now, transverse wave pulse, here's another example. So you can see that black box is going to move up and then back up again. So as the pulse travels through, you can see the direction of the propagation, and the pulse is going to travel up and down. So the particles are only moving up and down. They're not moving in any other direction. Now, we also have longitudinal waves, which is a wave traveling in which the particles of the medium move parallel to the wave velocity, also called a compression wave. So if we look, we have a spring here that's stretched out, and if we pull a couple of those coils back on the spring and we let it go, what's going to happen is we're going to have a compression of those coils traveling through that spring, and it's going to look like the middle part, as the pulse travels, is going to look like the coils are all bunched together, because they are, and those coils are just moving back and forth. So the front coil hits the next coil, causing the compression, but then the coil ends up moving back, so they just move right and then left and end up with no displacement. So a transverse wave pulse, an example of that would be waves on a string, as we're going to experiment with a lot in this video. A longitudinal wave is an example, is a sound wave. Other types of waves, earthquakes, are a combination of both transverse and longitudinal. An ocean wave is something called a surface wave, and light, that we'll talk about at the end of this series of videos, is an electromagnetic wave. As wave pulse, we're going to go through some vocabulary. So we have our wave pulse, and the pulse, first thing we're going to do is anytime you draw a pulse, you're going to draw the direction that that pulse is traveling by just drawing an arrow the way that the pulse is traveling. So that's the pulse direction. Now, the length of the pulse, left to right, that's called the pulse length. So we can measure the pulse length just by knowing how long the disturbance is. Anywhere the pulse is not traveling is called equilibrium. So anywhere along that string is going to be the equilibrium point. And then the height of the wave is called the amplitude of the wave. So measured from equilibrium to the highest point, regardless if the pulse is above or below. Now, the speed of a wave in a medium is constant. So that means that we can use this equation, that v is equal to d divided by t, where v is the speed of the wave propagating through a medium in meters per second. D is the distance the propagating wave travels in meters, so it might move back and forth along a string multiple times, so that's why we use distance instead of displacement. Now, the time that it takes to travel that distance back and forth, that's the time in the medium measured in seconds. Now, the speed of a wave is affected by the change in medium. So the density of the medium can change the speed of a wave depending on the type of wave. The more dense the medium can either increase or decrease the speed of the wave, and we'll discuss that in this series of videos. Now, in a string, the tension of the medium, so if we increase the tension of the spring, that can affect the speed, and the linear density, or mass per unit length, can also impact the speed of the wave in a string. Now, a sound wave can be affected by multiple things: the temperature and air pressure. So we're talking about the wave traveling through air. Temperature of the air and the pressure of the air would impact the speed. Now we're going to focus on the speed in a string. So the speed in a string is going to be equal to the square root, and the first thing is the tension. So as tension increases, that's going to increase the speed, but not a direct relationship because you can see it's under the square root. So it's not going to increase as great as the tension. So the linear density or mass per unit length is going to have an inverse relationship under the square root. So the heavier the spring, the harder it is to move that spring. So the disturbance traveling through it is not going to propagate as quickly the heavier the spring is. But if we increase the tension, that would increase the speed on the string. Now, wave pulses reflect, much like we saw with light in the last unit. So waves reflect or bounce back into the original medium when a wave reaches a boundary between two media. So a fixed end reflection is when the end of the string is fixed in place. So you can see this black dot is going to be our fixed end and does not allow the string to move. So as a pulse approaches that, what happens is that since the end of the string is not able to move, so then what happens is the pulse reflects inverted or on the opposite side and ends up traveling on the opposite side of the string. Now another type of end is called a free end. A free end reflection, the end of the string is able to move. So the black dot now can slide up and down the pole on the end. So as we send a wave pulse through, this moves up and down and then it reflects upright. So a free end reflection reflects on the same side of the string. So if it starts on the bottom, it stays on the bottom. If it starts on the top, it stays on the top. So we're going to talk about refraction of waves. Now we've been talking about one singular medium, but passing or transmission of a wave from one medium into another is what we're going to talk about now. So we have two strings here, a light or less dense rope that's represented by the tan thinner rope, and the heavier, more dense rope, the darker brown, thicker rope. So the more dense medium and less dense medium, we're going to see what happens to a wave pulse when it interacts at that boundary point. We know from our study of light, when light reaches a boundary, two things happen. It transmits into the new medium, and that's going to be a transmission on the same side for a transverse pulse, and some of it reflects. Now notice the reflection is on the opposite side. The light rope has a hard time moving the heavy rope, so it acts like a fixed end, so it reflects inverted. So from a light string to a heavy string, the pulse reflects inverted, but it transmits upright. And then notice as the pulses continue to travel that the light rope has a faster speed than the heavy rope because there's more mass per unit length in the heavy rope with the same tension because they're both pulled with the same tension. Now, if we have a wave pulse traveling in the heavy spring, well, again, we're going to have that transmission and reflection, but this time we're going to have the transmission on the same side, and the reflection is also going to be on the same side because the heavy rope is able to move the light rope easy, so it acts like a free end reflection. And then again, the pulses travel. So you can see that the pulses total amplitude is going to be the same as the original, assuming no energy is dissipated. Superposition of a wave. Now, what is superposition of a wave? Is when two or more waves are traveling in a medium and they encounter each other. So we have two waves, and I'm going to draw them in red and blue and show them just barely not at the centers overlapping. So what's going to happen is when the two of those wave pulses get to each other, the result of the wave is in the medium is the point by point sum of the individual waves. Now what that means is we go back, if we just take the amplitude at any point of the red and blue, we just add it together and we get the total of the amplitude, which is what gives us this purple wave pulse. And then as they continue, the red is going to travel to the right and the blue continues to travel to the left, and they pass through each other. So the wave pulses pass through each other, they don't bounce off of each other. And we say that the waves at the point where they're in the same spot are interfering with each other. And the interference types that we have is when wave pulses are on the same side of the string. So like we just saw, when the wave pulses are on the same side, they construct a much larger wave pulse. So we call this constructive interference when the wave pulse has a much larger amplitude. Now, we can also have wave pulses on the same side that have varying lengths or varying amplitudes. So if they have different lengths, what's going to happen is that you can see on the outside of the red, where the blue is not being interfered with by the red, nothing's going to change about the blue. But what happens is that it's going to look like the red is just stacked on top of the blue. So the purple that we have here, the red is stacked on top, and then they pass through each other. So this is a different type of constructive interference. Now, when the wave pulses are on opposite sides of the string, what's going to happen is at this point, they interfere with each other, but they're going to cancel each other out because they have the same pulse length and same amplitude. Now, when they cancel each other out, this is called destructive interference. And all we would see at that point, if we took a still picture, is just a straight line. So I drew that line in purple, so we know that's where the wave pulses are. And then the wave pulses would continue after that point to travel in the same direction they were before they interfered with each other. Now, if we end up with two pulses with different lengths, but yet the same amplitude on opposite sides, what's going to happen, again, the blue is not going to be interfered with on the outside of the red. So what's going to happen is going to look like if we take the middle of the blue and just pull straight down on it, and we pull that down to the equilibrium spot, what's going to happen is going to look like we're going to have two little wave pulses because the red ends up canceling out in the middle part of the blue and parts, and then they pass on. So this is an introduction to waves on a string. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X @Cavi Coaches.